Hello everyone. Hope I'm audible. I'm Sai Venkatakrishnan, PhD scholar in the Department of Computer Science and Engineering in IIT Madras. So this is week 6 live session, and so we'll be discuss. The agenda would be as follows. We'll be discussing some few questions which were asked in the previous offering of the same course last year. And the questions would be related to the week 6 video lectures, mainly pertaining to CPU scheduling concepts and the synchronization basics. So this will be the agenda. The main aim of these live sessions is to enable you to help you to understand the concepts and guide you in solving these questions so that you would be better equipped when you try to solve the current assignment questions that were released for week 6, right? This video will be recorded, so those who have missed out or uh, due to poor internet connection or something, you can very well go and watch the recorded lectures also. So let's start with the first question then. So which scheduling algorithm is non-preemptive? This is question 1. So we are given a list of scheduling algorithms: round robin scheduling, priority scheduling, shortest job first scheduling, first come first served scheduling. And out of these four algorithms, which one is non-preemptive? So non-preemptive, as in say one process P1 is being executed on the CPU, and some other processes like P2, P3, P4. These three processes are in the ready queue, right? And in this case, if P2 say has a higher priority, or it is somewhat faster, it has a short CPU burst when compared to P1, and it has to execute immediately. In a non-preemptive CPU scheduling algorithm, since P1 is currently being executed, no other process, irrespective of its priority when compared to P1, can stop P1 and get the CPU execution time slot for it. So that's the meaning of non-preemptive. So if P1 is currently running on the CPU, no other process other than P1 can can stop the process P1 and get hold of the CPU. So that's a non-preemptive scheduling, and the only case where the P1 can be stopped is it can voluntarily just give up its time slot only when it invokes an exit system call, or like a terminate system call, or the abort system call. So these are the only times that the P1 can give up its hold on the CPU. So this is what a non-preemptive scheduler is all about. So out of these four scheduling algorithms, which one is a non-preemptive scheduler? Any guesses? Is it round robin, or priority scheduling, or shortest job first, or first come first serve? Right. So let's go through the options one by one, and strike out which one are preemptive, and classify which one are non-preemptive. Okay. So round robin is the main concept of round robin is to um, have a time quantum. So this is what round robin is all about. So round robin is, you have say a time quantum of say 2 milliseconds. This is your time quantum, and if any process gets scheduled onto the CPU for execution, it can only execute for this 2 milliseconds. So P1, irrespective of burst time, say P1 has a burst time of 8 milliseconds and P2 of 3 milliseconds, and P1 arrived first and P2 arrived second, and irrespective of its priority or burst time, P1 will first execute for 2 milliseconds, that's the time quantum, and second again P2 will execute for 2 milliseconds. So in a round robin fashion, all the processes in the ready queue will be given a time quantum, a time share of that CPU for execution. And so this is like a fair policy, and the whole ready queue would be implemented as a circular list, or just the pointer would be moving through the circular list, and the first process that is coming would be given the first time quantum, and if no other process is there for contention, then that only process which is in the ready queue would be executed continuously until some other process gets added into the ready queue. So round robin scheduling by default is a preemptive scheduling, because P1 does not execute throughout, uh, uh, does not has hold over the CPU throughout its burst time. It gets executed on the CPU only for the specified time quantum duration alone, and once the time quantum is over and if it still has some CPU burst remaining, then it gets preempted and some other process gets scheduled on that CPU and executed in from the ready queue. So by default, it's a preemptive algorithm. So round robin is a preemptive, so it's a wrong choice. Priority scheduling is similar to not similar to round robin. The whole concept of priority scheduling is I'll just erase this. So the whole concept of priority scheduling is, say you have a say process P1, P2 and P3, and this came first, this came second, and this came third, and this has a priority 3, this has priority 2, and this has priority 1, and say like lower the priority, lower the number, higher the priority. So assuming this is the case, and since P1 came first, P1 would be scheduled onto the CPU first. But since this is a priority scheduling algorithm, if P2 comes next, and P2 has a higher priority when compared to P1, so P1 would be preempted, and P2 would start execution. And now once P2 starts executing, we see P3 also coming into the ready queue. And once the scheduler sees that P3, a higher priority process compared to P2, is present in the ready queue, it preempts P2 also and schedules P3 to get executed on the CPU. And now P3, while executing, it doesn't get any other higher priority process on the ready queue. And what happens is that the P3 continues throughout its CPU burst time, and once P3 is over, the next priority process, that is P2, starts execution, and followed by P2. Once P2 is completed, P1 starts execution. So by default, this priority scheduling algorithm is a preemptive algorithm where a higher priority process, say P3, would preempt a lower priority process P2 or P1. So this is the default behavior of a priority scheduling algorithm, and so this is not non-preemptive, so this is also preemptive. So A and B options are ruled out. Now we'll see shortest job first scheduling. So in shortest job first scheduling, the whole concept is SJF scheduling algorithm. The whole concept is, say we have a P1, P2 and P3, and if the CPU burst time is as 4, 2 and say 1. So this is the CPU burst time, and the arrival is in this following order: P1 followed by P2 followed by P3. So this is the arrival order, and now say so first P1 gets scheduled onto the CPU and it starts execution. And now when P2 arrives, the shortest job for scheduler can be of two types. It can either be a preemptive version, okay. I'll just do this. So it can either be a preemptive version or it can be a non-preemptive version. So that's the uh, both the variants can be implemented on shortest job first. So when P1 is executing, P2 will arrive, and in a preemptive version, what happens is A shortest job first means the one having the shortest job would be given higher priority. So here P3 is having higher priority when compared to P2, and P2 has a higher priority when compared to P1. So when P1 is executing, P2 arrives and it has a shorter CPU burst time. And now in a preemptive version, P1 would get preempted and P2 would start executing. And when P3 arrives, P2 would get preempted and P3 would start executing. Once P3 finishes execution, the next shortest job would be P2 followed by P1. So this is the preemptive version of the same shortest job first scheduling algorithm. In a non-preemptive version, what happens is that instead of the currently executing process getting preempted, say P1 is currently executing, and the next it does when P2 arrives onto the ready queue, it doesn't preempt P1 on seeing that P2 has a shorter CPU burst time when compared to P3. Instead, it completes P1's execution, and once P1 completes its execution, the next process, whatever it selects from the ready queue, would be the shortest job first. So now instead of selecting P2, which has 2 CPU burst cycles, it will select P3, which should have already arrived by the time P4 completes execution. And P3 would be of 1 CPU burst cycle, it is the shortest job, and this should be scheduled on the CPU, and after this, P2 would be scheduled onto the CPU. So the shortest job first has both a non-preemptive version, also a preemptive variant. So both the variants are applicable. But in this question, if you note, they have specifically asked which scheduling algorithm is non-preemptive. So for sure, which one is non-preemptive? As in, it shouldn't have a preemptive variant of the scheduling algorithm. So option C is also ruled out. And in this case, the last option is the last option is first come first serve scheduling. So first come first serve scheduling is very simple. Whatever process, say P1 arrives first, followed by P2, followed by P3. If this is the arrival order, then whatever came first, P1 arrived first, so this will be given execution. This will be scheduled onto the CPU, and once P1 completes execution, whichever came second based on the arrival time, P2 came second, this will be scheduled onto the CPU, and once P2 completes execution, P3 will be scheduled onto the CPU. Very simple algorithm. So the nature of first come first served is whatever came first, just go and execute on the CPU, irrespective of its priority or the shortest job remaining, or all those things are not considered. Whichever came first is executed on the CPU. So option D is the correct answer, which is a non-preemptive version, non-preemptive scheduling algorithm. Always is first come first serve scheduling algorithm. So any doubts in this first question? So option D is the correct answer. If there are no doubts, we'll move to the second question. If you have any doubts, you can unmute yourself and speak, or you can just mention in the chat message. Right? Okay. So we'll move to the second question then. Among all the CPU scheduling algorithm, which one is the most simplest one? So which one is the most simplest one among the 4 CPU algorithms? The most simplest one, whether it's first come first serve, SJF, that is shortest job first, or round robin, or none of the above. Some other scheduling algorithm is more simpler. Is simpler. Any guesses which one is the correct answer? Right. So we will go through the options one by one. So first of all, let's understand the question. What makes a CPU scheduling algorithm simple? What are the various aspects? One. So what's the notion of simple over here? So one, the selection from the ready queue, selection logic. The selection logic from the ready queue, that should be simple. Second, the data structures that you use for maintaining that you use for maintaining the ready queue. So this includes like when a new inserting a new process when it is ready, deleting the process when it completes execution, and then selecting the correct process, right? So these are the various things, and also the other thing is the memory overrides and the selection logic. So memory override one, and so this includes like say for each process what all information you have to calculate. For example, in so this includes like the metadata maintained. So for example, if you take a priority scheduling algorithm, the metadata would usually involve, so for each process, which is the priority involved, what's the priority of that process when compared to the other processes. In shortest job first, you have to somehow estimate how many CPU burst cycles are still left for execution by that process. So these are all some metadata that has to be maintained, and for predicting that cycle count or all those things, some CPU some logic has to be executed. So all these are like memory overheads and execution overheads. So that is what memory overheads and metadata is all about with respect to a scheduling algorithm. And the selection logic, say in SJF, how do you select a process from the ready queue? Whichever process has the shortest job first, that gets selected from the ready queue. That's the selection logic. In a round robin, whichever process is next in that circular queue, that will be executed for that time quantum. In a priority queue, in a priority scheduling algorithm, you will select the process which has the highest priority among all the processes in the ready queue. That's the selection logic. And now in the data structures used for maintaining, you can use any data structure. So, and also the final thing is whether it's a preemptive one or a non-preemptive one, right? So excuse me. So preemptive version means even if that process still has some burst cycles to execute, it will get preempted context which will occur, and the some other process will be scheduled onto the CPU and get executed. That's the preemptive version. So based on these four policies, we will see which one of the given four scheduling algorithms is the most simplest one, right? So first let's take round robin. First let's take SJF, right? So SJF, what's the selection logic? Selection logic is for SJF, it's the shortest job should be selected. And for selecting that, say you have a queue or some, this is the selection logic, the shortest job has to be selected from the ready queue. And what data structure should be required? There are many data structures you can use for shortest job, and since um, the main to minimize this selection logic, right? So let's say if some process P1 is getting executed and the need cycle or something, the kernel has to, the scheduler has to see whether some other process having a shorter job is waiting in the ready queue. Assuming that's a preemptive version, we should see some other process whether it's waiting in the ready queue. Even in a non-preemptive version, once P1 finishes execution, it will see the shortest job process which is waiting in the ready queue. So if you are having a the ready queue implemented as a linked list, what happens? What happens is you have to traverse the whole linked list and see which one has smallest, the shortest job CPU burst time associated associated with that process. You have to find that process and then schedule it on the CPU. So you have to traverse the whole linked list, and traversing a linked list is very expensive operation, since you have to load the memory, and it will be like a structure, right? A structure, a linked list structure. You should be loading the next pointer, and there will be many memory operations. And say if say 100 processes are there on the linked list, you will be traversing that 100 element linked list until, and then you have to find that minimum, the shortest job process, and then schedule it on the CPU. And this you have to do every, in a preemptive version you have to do it every clock cycle, because any clock cycle a new process might arrive, and the scheduler has to check whether it is a shortest job first or not. So it's an expensive scheduling algorithm. And when compared to linked list, since linked list is expensive, some implementations they use a red black tree, where the ordering of the nodes themselves, that's the process which are present in the ready queue, would be ordered in such a way that all the minimum, the shorter job processes would be in the left side of the tree, and the more heavy side of the heavy processes which have higher CPU cycles would be present in the right side of the tree. It would be like a slightly balanced tree, and an external pointer would be pointing to the process which has the shortest job first, right? So these are like the data structures which are used underneath to maintain this ready queue would can be changed based on what criteria, what logic we have to optimize. So if I have to optimize the selection logic uh, with respect to a shortest job first algorithm, I can go with a red black tree, because selecting the next shortest job process from the ready queue would be very simple when compared to traversing the whole linked list, very expensive operation. So this is what SJF is all about, and based on these three factors, right? These four factors, if you say, SJF is expensive. It's not simple actually. It's not simple. It's somewhat tricky to implement, right? And now, if you see a round robin, what is round robin all about? If you see round robin, um, simple. It just has a circular queue, and the processes would be maintaining in the circular queue, and whatever this is the ready queue, it's maintained as a circular linked list, and whichever process, the selection logic, how it will be selected, whichever is next in that linked list, the circular linked list, that process would be scheduled onto the CPU. And for how much time it would be scheduled is, it would be scheduled executed on the CPU for that time quantum duration which is specified by that scheduling algorithm. So the data structure used for round robin is very simple, a circular linked list, and the metadata associated is very simple. You just have to maintain the time quantum and those things, and also for inserting a process or deleting a process also very easy. You just have to move the pointers in the circular linked list to indicate that the process has finished completion or all those things. Excuse me. So this is all about round robin, but the tricky part in round robin is what this time quantum is all about. What should be the time quantum? Say if you take a high value for this time quantum, say 100 milliseconds, and assuming that your process, all the processes that are present in the ready queue themselves have some CPU burst cycle on the average of 50 milliseconds. So in that case, if you specify a time quantum of 100 milliseconds, this round robin scheduling algorithm transforms itself into a first come first served scheduling algorithm. Because the time quantum is so huge, and by the time the time quantum expires, the processes themselves would have finished executing its logic and given would have released control over that CPU. And if you place a very small time quantum, right, say just 2 milliseconds, and the average is 50 milliseconds for the processes that are present in the ready queue, what happens is the number of context switching in that round robin fashion, for every 2 milliseconds you will be having every 2 milliseconds there will be a context switch. And as you all know, context switch means you have to store the registers and then store the stack pointer, all those things, then restore back the registers, and all those things will be involved in a context switch, and it will be involved a user to kernel mode switch and all those things. So that will be in expensive operation. So if the time quantum is very small, the number of context switches would increase so much that the round robin scheduling algorithm would have a high waiting time, and also the completion time would be very high. So the tricky part in round robin scheduling algorithm is how we have to estimate this time quantum variable. So this is the most tricky part in the round robin scheduling. But compared to SJF, implementing the round robin scheduling is simpler, right? But the tricky part is getting this time quantum variable properly. So this is what the round robin scheduling algorithm is all about. The last one that is left is FCFS. Compared to round robin scheduling, it's very easy, because all you have to maintain is a queue. There is no metadata that is required, just a normal first in first out queue. That's what is required for FCFS. And insertion or deletion or the selection logic is also simple. Whichever came first, arrived first, that will be executed on the CPU. So this is the simplest algorithm, and so based on these parameters all, the FCFS is the simplest algorithm. The other RR is also somewhat simple, but you have to correctly identify what the time quantum value should be to make it efficient. That round robin scheduling algorithm. SJFS is a bit difficult to implement, and the selection logic, all those things should be a bit involved when compared to FCFS and RR algorithm. SJF, the shortest job first algorithm. So FCFS is the simplest one. Any doubts in this question? What factors we used to determine whether a CPU scheduling algorithm is uh, easy to implement or somewhat involved, difficult to implement? So any doubts? If no doubts, we can move to the third question in that case. Right. The SJF algorithm can be, four options are given. There is only a preemptive version, a non-preemptive version only. The SJF, the shortest job first algorithm, can be both preemptive as well as non-preemptive. And third, none of the above. So which one of the following options are correct with respect to a shortest job first scheduling algorithm? So as we had mentioned, discussed previously in both the questions 1 and 2, the shortest job for scheduling algorithm can be both preemptive as well as non-preemptive, right? The the reason being, it can either be designed in either way. It can be designed in either way. The shortest job first algorithm. In a preemptive version, if a process which is having a shorter CPU burst gets scheduled onto the ready queue, it gets inserted, gets added into that ready queue, then the currently executing process would be preempted, and that shorter job process would be scheduled and executed on the CPU. That's a preemptive version. Non-preemptive version is nothing but you uh, don't preempt that currently executing process, but the next process whatever you select from the ready queue would be having the shortest job with respect to all the other processes that are present on the ready queue. So the SJF algorithm can either be a preemptive variant or a non-preemptive variant. So option C is the correct answer, and the other options are wrong. Right? Any questions in any doubts in question 3? If not, then we will move to the fourth question. Which is the most optimal but difficult to implement CPU scheduling algorithm? Whether it is the shortest job first, or FCFS, or the round robin scheduling, or none of the above, some other algorithm is present. Right. We'll see one by one. If we take the case of FCFS, the question asked is which is the most optimal but difficult to implement. So we'll see which one is the most optimal and a difficult to implement algorithm. Right. We'll concentrate on this aspect, most optimal, because difficulty is separate. The optimal version would be, we should look at it separately. So FCFS, is it an optimal version? No, because one thing is whatever process came first, based on the arrival time, that would be executing on that CPU. And now if say a process with a long CPU burst, say 10,000 milliseconds or something, gets scheduled onto that CPU, what happens is that all the other processes that are waiting in the ready queue, say IO bound process, which has a very short CPU burst cycles, those should all be waiting for this process which came first and got hold of the CPU and would be executing for 10,000 milliseconds. And since FCFS is a non-preemptive version, so this is non-preemptive, and since it's non-preemptive, none of the processes can preempt that long executing process for 10,000 milliseconds, and all the other processes have to wait irrespective of its priority or whether it has a shorter CPU burst when compared to the currently executing process. Nothing is taken into account. So this is something called as the convoy effect. So like a long convoy, right? You see convoy of cars or something, right? Like a long convoy, it is present. It is getting present in the ready queue, waiting for this long executing process to finish execution to get completed. Right. So FCFS is not optimal version. It's not optimal scheduling algorithm. So FCFS is a wrong choice. Compared to SJF and round robin, right? Round robin is somewhat of a fair version of the same FCFS policy. So fair as in to avoid this convoy effect, right? To avoid convoy effect and to have fairness among all processes, irrespective of its priority or whether it has a shorter job or something. Based on its arrival, it will be inserted into the circular linked list, the ready queue, and then each process would be given a time share of that CPU for that specified time quantum, which is fixed for all the processes. For that specified time quantum, the process would be given control of that CPU. It would uh, it would get executed, and once the time quantum is over, the next process present in that circular queue would get scheduled onto that CPU. So round robin is a very fair version, and for it makes progress for sure, and it's a fair version. But whether it's the optimal, no, because Say you have you consider the case of a real-time operating system which is normally used. So I'll just erase this part. Right. So say you have a real-time operating system which is usually used in automotive engines, automobiles, and most of the automobiles are now having some sort of real-time OS or something, right? So in this thing, say when you apply your brakes or something, that signal gets transferred via the internal circuitry, the MCUs, right? All those things. It gets transferred and an interrupt is raised or some process has to get executed. Say some brake process which is really in a real time system, or which is like life and death matter situation, right? So in that case, the brake process should be given a higher priority, and whatever process is currently executing should be stopped immediately, and the CPUs should be executing this break process. But in a round robin fashion, what happens is if this break process say comes fifth onto the ready queue on the arrival, after executing all the four processes for its specified time quantum, then only the break process would get a hold of the CPU for execution. So in a real-time OS on these things, round robin it does not fit. It's not optimal, and not only real-time OS. Even in an interactive version, say you are using some GUI application. So once you say click on that um, click on the dialog box or something, you have to immediately, as a user, you expect immediately some effect to happen, some action to take place, and the response time has to be very small. Response time, as in the response time as in the first time slot where that process which is present in the ready queue is given control of the CPU. So that's the response time. So smaller the response time, better the user experiences. So in an interactive system, the smaller response time would usually be required. So whatever the user is viewing, that should be given a higher priority when compared to all the background processes that the system is executing. So say you have a one GUI application that you're which is like a gaming application, and in the background you're having some other processes such as say email thread, all those web server or some not web server, say some non-important processes. Now if this GUI as well as background processes are given the same priority and executed in a round robin fashion, it is not optimal because the response time for this gaming should be very high. In a round robin fashion you won't get such a fast response time. But in a shortest job first scheduling algorithm, say this gaming thing, it needs a higher response time. It based on its priority, it should be given more priority, right? This GUI application. So SJF is a optimal version when compared to FCFS and RR. A tricky part in this question is um, SJFS is definitely optimal because in a real-time OS or this interactive operating system, these processes, compared to FCFS and RR, SJF would have a better response time, and also based on its priority, the most important processes that get executed on the CPU first when compared to the less important processes. And also you don't have this convoy effect where a list of IO bound processes are waiting for the a long process to get executed on the CPU. But one thing is, out of these given three, SJF is better, but there are other optimal versions of SJF also. Um, Say priority scheduling or multi-level scheduling based on how their design is, and the variant which type of priority queue and the say in a multi-level queue and all those things. Other complex scheduling algorithms are present, but the basic tree are these three, SJF, FCFS and RR. So it can actually, in my opinion, it can either be option D or option A, but given the lecture contents that you have seen till now, and given these three options, SJF, FCFS and RR, it would be safe for you to go with option A, which is the actual correct answer based on the answer key. There can definitely be other optimal algorithms which are difficult to implement, but out of these three, SJF is the correct answer, and you better stick with option A, which is SJF, right? Given, since this usually it's an MCQ pattern and you don't get to key in a specific algorithm, you better stick with SJF. So SJF is the correct option, and which is the most optimal and difficult to implement. So any doubts in this question 4? If not, then we'll move forward to question 5. Right. There are 6 processes in which the arrival order of the processes are like P1 came first, then P2, and in the same way P3, P4, P5, and finally P6 arrived. And we have the given burst times over here. What's the average waiting time for the FCFS policy? So we are given some values and we should find the average waiting time. So let's draw the Gantt chart and see calculate the waiting time for each process, and then we'll get the average. So P1 came first, so P1 will be given P1 will be given execution. So till for 9 time units, P1 would be given execution, and followed by that P2 would be given execution because P2 next came. So that is for 1 execution. So this is for 9, this is for 1, and followed by this P3 came next after P2. So that is for 14. So 24, because 10 plus 14 for 14 time units. P3 gets executed. That's the CPU burst time, and then P4, P5, and P6. And what's the completion time for these processes? So 24 plus 2. That's the for P4 burst time, which is 26, and followed by P4. There is P6, that is 6 burst time. P5, which is having burst time of 6. So plus 6, 32. And then you have P6, which is executes for 20 cycles, which is 32 plus 20, 52. So this is the Gantt chart. Now to find the average waiting time for each process, we'll find the waiting time, and then we'll find the average, right? So for P1, it is 0 because it immediately gets executed on the CPU schedule. There is no waiting time. So P1 is 0, and for P2 you wait for 9 cycles, because for 9 milliseconds you wait, because P1 has to finish execution and then P2 gets scheduled onto the CPU. So for 9 milliseconds you wait, and for P3 only once P1 and P2 gets executed, you schedule P3 for execution on the CPU. So P3 waits for 10 milliseconds, right? And followed by this P4, which has to wait for which has to wait for 24 milliseconds, and followed by that P5, which has to wait for 26, followed by that P6, which has to wait for 32 milliseconds. And now to find the average waiting time, we get the sum of all these things divided by 6. So 19, 24, 26, 32. So 9 to 11, 4, 15, 15, 6, 21. So 5, 1, 6, 2, 8, 101. So this is 101 by 6, which is nothing but 6, 41. 41, 636, and 5. which is 8, so around 16.8. So out of these four choices, 16.8 is the correct answer. So for 16.8 milliseconds, right, you would be that's the average waiting time. So we first drew the Gantt chart, and then we saw at what time each process gets scheduled onto the CPU, and that whole time till it's present in that ready queue. Um, from that ready queue till the time it gets first scheduled onto the CPU, that time is the waiting time for that process. And we take the sum of all the waiting times for all the processes, and then take the average, divide by 6. That's the average waiting time for these 6 processes when come with respect to first come first serve policy, right? Any doubts in this question? If not, we'll move to the sixth question. So consider the following table. Um, so we are given three processes, A1, A2, A3, and we are told that we should find the correct completion order. So in what order will these processes get completed given this burst time and the arrival time, under two scenarios. First scenario is we have this first come first serve, and second scenario is round robin, where the time quantum is for two time units, that is 2 milliseconds, right? So given this scenario, what would be the order in which the processes would finish completion, would be completed in which order? Um, Whether A1 would get completed first, or A2 or A3, which order when compared to FCFS and a round robin scheduling algorithm with a time quantum of 2 units. Right. So first, let's see FCFS. FCFS is all, but based on the arrival, it gets scheduled onto the CPU. So if you see the arrival, A1 came first, so A1 will get completed first. Then A2 came, so A2 will be second, and finally A3 came, so A3 will be second. A3 will be the third process to get completed. So out of these four options, A, B, C, D, option A is completely for sure wrong, because the FCFS thing is wrong. A1, A3, A2 is the wrong order, because A1 followed by A2 and then A3. In this order only the processes get completed. So that's the completion order with respect to FCFS. So B, C or D is correct with respect to FCFS. And now we will see for the round robin scheduling algorithm. So let us draw the Gantt chart, which would be easy to explain. The round robin algorithm, how it works is, first A1 is present in the ready queue based on its arrival time. So it executes, and while it is executing, at once the time quantum 2 finishes, by the time A2 gets inserted into the ready queue, right? And now A2 gets scheduled, and since A1 gets preempted, A1 is again stored in the ready queue as next to A2. So at time unit 3, actually A3 arrives, but A3 won't get executed immediately. Instead, it would be actually A1 getting executed after A2 based on the order in which it's present in that circular queue. So now A1 would be executed, and once A1 finishes execution, it will be A3 actually, right? And now after A3, it's actually A2, okay? And once A2 finishes execution, it will be A1 present. And by this time A1 would have completed execution, and now it will be again A3 which is getting executed on the CPU, and this will also be completed, and then finally again A2. So first A1 would be completed, and then A3, and then A2 for the remaining time, because the time quantum, how it is split for two units, these will be scheduled, and accordingly that it will, A1 would have completed its allotted CPU burst time first, compared to A3 and A2. So option B is the correct answer. Okay, so this is how the round robin scheduling works, and based on that, option B is the correct answer. So any doubts in this? If not, we'll move with the seventh question. So consider the set of processes P1, P2, P3, P4, P5, P6, and you have the burst time and the priority, and assume they all arrived in this order: P1 followed by P2, P3, P4, P5, and P6. What will be the average waiting time in a priority based scheduling? So let's draw the Gantt chart. And one thing to note is lower number implies higher priority, right? And let's see, let's assume that all these six processes are present in the ready queue, and the scheduler has to pick one. Okay, um, so based on the since it's priority scheduling algorithm, first P6 should be scheduled. It has the lowest priority, so that will be for 6 burst time units. Okay, and followed by P5, that will be for 1 unit, and then it is P6, sorry, next is priority 3, which is P1, which is for 27 units, and followed by that, which is P3, 27 plus 7, which is 34, and then you have once P3 is over, which is next is P2, and followed by that we have P4. So P2 executes for 3, so 37, and P4 executes for 8, which is 45. Right. So this is the completion times based on the Gantt chart and this priority scheduling algorithm. Now we'll find the average waiting time. So P6. So let's start from P1. So the average waiting time for P1, the waiting time for P1 is it waited for 7 units, and for P2 waited for 34 plus um, P2 waited for 34, P3 waited for 27, P4 waited for 37, plus P5 waited for 6, and P6 for 0 units it waited. So we'll take the sum and then divide by 6, right? So 34, 27, 7, 37, 6. Okay, we'll just take the sums. Right, so the sum is 111, so sorry, 111 divided by 6. Okay, so that is around 18 point something. So out of these four options, option B is the correct answer, the other options are wrong. So this is what the Gantt chart for the priority scheduling algorithm looks, and this is the average waiting time, 18.5 milliseconds. So this is the correct answer. Any doubts in the way this, how we find the average waiting time and all those things? Right. If not, let's move to the eighth question. So in which of the following options below only one process at a time is allowed into its critical section among all the processes that have critical sections for the same resource? So we are looking for a term which corresponds, which has the following meaning, right? So which one of these is a term, this meaning, this para, whatever is given, which of the following terms actually represents this, the concept behind this? Okay, so whether it's deadlock, no for sure, because deadlock is a different scenario, which is like two processes are waiting for some resource that the other process has locked. So that's the meaning of deadlock. And whether it's synchronization, no, synchronization is with respect to say some shared variable, and two processes have to um, go and increment or do some operation on that shared variable in a synchronized way as if they had executed sequentially. That's what synchronization is all about. Let's come to option B, which is mutual exclusion. So mutual exclusion concept is nothing but you have a critical section, and multiple processes, say P1 to Pn processes, they want to get enter the critical section, but the condition for mutual exclusion is only one of these processes can successfully enter the critical section, and only one process can be active in the critical section at any given time. So that's what mutual exclusion is all about. So this term mutual exclusion corresponds to this para which is mentioned in the question. So option B is the correct answer. Synchronization is solved by mutual exclusion. One of the conditions in solving synchronization is mutual exclusion. So attempting to write that shared variable should be done only by one process at any given time, and the other processes should not try to uh, change that shared variable or read or do something on the shared variable. So mutual exclusion principle is applied to solve the synchronization problem. So option B is the correct answer. The other options are wrong. Any doubts in the question 8? Right. If not, we'll move to the ninth question. So which of the following solutions for critical section problem? So which of the following are the solutions? Whether it's mutual exclusion or progress or bounded weighting. So based on the problem, right, the critical section problem, what this means is in the critical section only one process can be active, and only one process can gain entry, and the other process should be waiting. So this is the main goals of the critical section problem. And if you have gone through the lectures, in fact all these three concepts, mutual exclusion, progress and bounded weighting, all these three principles are required to solve this critical section problem, because uh, mutual exclusion is important for this critical section, because only one process can gain entry into the critical section and is active at any given time. So that is what mutual exclusion is all about. And progress is say if multiple processes are there, and if none of the only one process wants to gain entry into the critical section and the other processes do not want to enter the critical section, then your it should be the algorithm should be designed in such a way that that waiting process should immediately be given entry into the critical section, so it makes progress. So that is the importance of this uh, principle. And the third one, bounded weighting, is say you have multiple uh, uh, you have multiple these things what multiple processes waiting in the queue to gain entry into the critical section. It is not that it is the waiting time should be bounded, it should not be infinite. It cannot be like a non-deterministic value, it should be a bounded waiting. So all these three put together only solve the critical section problem, are required for the critical section problem. So the correct option is option D. Any doubts in this question 9? If not, we'll move to the last question. So mutual exclusion implies that if a process is executing in its critical section, then the other processes must be executing. Um, must be executing. Or option B, if a process is executing in its critical section, then all the resources must be blocked. Or option C, only one process can be executing in its critical section, or option D, none of the above. So which one of the following terms actually corresponds to mutual exclusion? The answer is pretty simple. It is option C. Um, Only one process can be executing in its critical section, and no other process must be executing in the critical section. So option C is the correct answer. The other options are not relevant to mutual exclusion. So option C is the correct answer. Any doubts in this question? So if you have any doubts, you can post it in the chat box, or you can unmute yourself and ask, or you can post in the discussion forum of the OS course also, right? And just a quick this thing recap. So this round robin thing alone, round robin scheduling, I'll just explain it clearly again. Those who want to leave can leave. Sorry for the extension. This is a recorded session, so you can feel free to leave and look at the recorded video also. So in a round robin, this is the ready queue, which would be implemented. So this is the ready queue. So first the arrival time A1 gets inserted, and now A1 gets scheduled onto the CPU for 2 time quantum units, and by the time A1 finishes, A2 would have arrived. So now A1 gets deleted, now A2 would have arrived, and what happens is A1 gets preempted and it gets added into the ready queue, and now A2 gets executed on the CPU for 2 time quantum units. And by the time A2 finishes, A3 would have arrived, because it is like now 4 units have gone. So at arrival time 3, A3 comes. So that gets added into the ready queue. And once this 2 time quantum is over for A2, A1 gets scheduled onto the CPU, and A1 gets scheduled, and A2, since it has remaining some it got executed for 2 units alone, and remaining is 5. So now A2 remaining is 5, it gets added to the ready queue again, the last position. And now A1 gets executed, and once A1 finishes execution, finishes the time quantum execution, it sees that A1 has 5 units in total, but only 4 got over. So again A1 is added at the end of the queue with the remaining time quantum 1, and the next in line is A3, so that gets executed for 2 time quantum. And A3 still has some 1 cycle left, so again it gets added into the ready queue. And now A2 gets scheduled onto the CPU, and for time quantum 2 units it executes on the CPU, and since still it is remaining, this gets added again at the end of the ready queue for remaining 3 cycle units. Now A1, what happens is it finishes execution in this time quantum itself, because only 1 unit is remaining. So for 1 unit time alone it finishes, it completes execution, and immediately it doesn't get inserted in the ready queue again, because it completes execution. There is no CPU burst left for it to complete. Everything is over, so A1 gets deleted from the ready queue, and now A3 again gets scheduled, and A3 also, within the time quantum, just 1 time unit is required for execution, and it will finish execution, and it doesn't get added at the end of the ready queue again. So A3 also finishes execution, so this gets complete over here, and in the same way this gets complete over here. And now finally A2, there is no other process in the ready queue, so irrespective of the time quantum, so for 3 units A2 completes executes on the CPU and completes execution. So first A1 gets executed, and then A3, and then A2. So this is the order in which these 3 processes complete execution. So with respect to that, A1, A2, A3 and A2, so this is the order, and for FCFS, A1, A2 and A3. So option B is the correct answer. Right. Hope you understood the concept better this time while explaining. Um, yeah. Right. Process is. Can you just come again? So, I read your question. One, zombie versus orphan. Yeah, 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 yeah. I responded. Yeah. So, as in, say you have a parent process, and parent forks the child process. Okay, and now the child is executing, and what happens is this child, the parent sleeps for 15, say 50 milliseconds, and the child finishes execution within 10 milliseconds. And now, after this 50 milliseconds, so only the parent again wakes up and executes this wait system call. Okay, so now the child process, what happens is once it finishes execution after 10 milliseconds, it calls exit, it terminates. So what happens is the child exits, but still its process entry is active because the parent process was sleeping for 50 milliseconds, and it invoked a wait system call only after that. So till this time the process entry would be active. So in this case, right, this is one scenario where you this like explaining a zombie process. It in this case, say you don't have a parent itself. Um, no, no, no. Without a parent also, say one process P1 is executing, and when it exits, right, immediately that process entry won't be deleted. There would be a small gap, right? Because once it exits, it has to call that kernel scheduler, and it has to delete from that ready queue. Like at least like 1 millisecond, it would be still present in the thing, right? In the ready queue, that entry would be active, right? Until all the resources allocated with this process one gets deleted, gets inactivated. Till then, the process entry would be active only. So no, no. Orphan process is totally different, where it only happens in like a parent-child relation, where the parent finishes execution and does not wait for the child. So the child is like, doesn't have a parent who is waiting for it, and the child does not know what to do once it gets finished. Once it finishes execution. So that's what orphan is all about. Zombie is when just take the literal meaning of zombie, right? You are living, but the entry is active, but you are dead. So that's the literal meaning of zombie. They have just used it. The process is dead, but the entry is alive. That is zombie. No, no. So in the zombie one, see in the zombie one, I took this explanation where P1 is finishes execution, and there is one small time unit for which a process entry is still active. Here P1 does not have any parent. So zombie does not. Zombie process is just take this definition literally. That is what a zombie process is all about. Um, It can take place in this scenario, like when a parent sleeps and the child exits beforehand, or it, no. See, P1. No, no. it is not, this P1 is not an orphan because it has no parent actually. First of all, this is not a child process itself. No, no. So in this case, right, what I meant is P1 is a process, and say this process you it, it is not you don't get this process via like a fork system call or something. Assume that this is the first process or something like it. It's not. It's this is not a child process. Take it like that. So where's the concept of orphan then? Only when a parent process, say P1 forks some other process, then P1 is the parent of P2. In this scenario, yeah, right. Okay, in the slide is it? So if no parent waiting did not invoke, if parent did not invoke wait, uh, parent terminated. Right. So there is a difference between a parent terminated and parent waiting. So only if a parent. So in this case, yeah, yeah, it's there. The parent is there in the system. So in that case, it's a zombie. The parent terminated means the parent is not in the system. In that case, it is an orphan. So that's the difference. Right. It is an orphan, right? Because uh, parent leaves, as in parent terminated, right? So that's what you should take. So it is orphan. Yeah. Okay. Thanks, Shashikant. Uh, right. If no other doubts are there, then we can end this session. Thanks, everyone. Yeah. Thank you. Yeah.